So today we will talk about LCD TFT in the outdoor environment. That means we will talk a lot about the contrast and the brightness of a display and the reflections. How does it influence what we see? Because what we see is a contrast actually at the end of the day, not the brightness of a display. And the contrast is derived from the numbers that is like brightness of a display and reflections. And we will see how does it work and what to do to have it best possible. So here we have agenda for today. So as I said, we'll talk mainly about the contrast because this is the key factor to see the image clear and the content clear. But we will talk also about the sunlight, how does it influence, and of course every light influence the display and how we see it. Then we'll talk about reflections, brightness, and how do we operate this in the different temperatures, because there are solutions to use displays in like outdoor environment, that means in very high temperatures or very low temperatures. So this is a little bit separate from the contrast. It's connected with the outdoor TFTs, yes? So contrast is one thing, so with display we need to see the content, but the other thing, it need to work in the wide range of temperatures. And the solution here is a little bit different than the contrast. So let's start with the contrast ratio. It's a parameter that you can find easily in every display datasheet. That is something that we measure in a factory and give, let's say, to the customer as a reference number. So the contrast that we see in example datasheets here from our datasheets are, you know, couple of hundreds, and I would say this is the standard for industrial type displays. Let's say from maybe like low end will be 300 to 500, and high end will be maybe 1,000 to 2,000 as a value of contrast. And it's a very good number. If we will have a display with such high contrast, then we see image perfectly actually. It's a little bit different number than you can see if you will buy a TV. If you will go to the let's say specification of a TV, you may find the number like even 1 to 1 million of a contrast. But it's usually a little bit tricky number and not the number that is, let's say, particularly most important to have. Because as we will see on the next slides, the real contrast, like in real world, it's a way lower than the numbers even here for industrial, and you know, could be like, you know, hundreds, thousands times lower than you can see in a TV specification, and still you see the contrast clear. They measure it different. Maybe I will talk about it later, yes? So basically, first thing, what is the contrast? Is just the ratio between the bright side or the bright parts of a display to the dark parts, yes? So this is like pretty simple to measure. So we just measure the brightness. If we will if we imagine this is a display, we can measure the white part, how many candelas is there. Let's say it will be 1,000 candela display or something like that. And then having the backlight on and the pixels blocked, that is the black color here, we will measure the brightness, because some brightness is here, of course. If we will, for example, switch off the light, make the display entirely black, but not switch off the backlight will be still on, we will see that it's actually, there is some light coming out of it. Because the pixels are not perfect, they are not perfectly blocking the light. So maybe it could be like we have 1,000 candela here and maybe 10 candela here, yes? So because it's a very big difference between them, we still see this black and this we see white, but actually this is not the perfect black. In some TVs, we spoke about it last time, about OLED TV from LG, for example. There the contrast can be very high, because when the OLED TV has the pixels off, they are not emitting any light. That means they are really black. That's why I told you, go and see this kind of TV, because it's a different kind of experience. If you have a dark background, it's really dark, it's black. It's not something that we are used to from normal TV that is a TFT. So this black is no black. That's why we have some contrast that is like, you know, couple of hundreds or 1,000 or 1,000,000, depend how you measure that. Yes. So going more into the details, we talk something like the real contrast. We call it effective contrast ratio. Yes. So in our data sheet, we will have a CR, that is a contrast ratio. It's like a perfect condition factory value. That means we measure it in a dark room without any reflections, and we just measure the white part of the screen and the dark part of the screen without any reflections. But in real world, we have a light, like in this room we have a light, or outdoor we have a lot of light. That's why we'll talk about it more, that will be connected with the sunlight. Then we have reflections, like every surface reflect. If it's not like a true black surface, then we have reflections. And reflections are adding the brightness to the surface. Yes, so it's adding the let's say to the bright part, but it's adding to the black part, like the dark part, which is destroying the contrast, or like lowering the contrast a lot. So here we have some numbers, and as you see, they are very, very low. Yes, comparing to the data sheet that we have seen before, it was like 1 to 500, or I even told you 1 to 1 million from a TV maybe specification. And here we have only 1 to 2 or 3, 4, and up to 20. And you can see that like reasonable, maybe between 5. 5 is okay contrast, and most of the things we see something like 5 to 10. As you see, like if it's 10, it's very readable. Yes, and if it's 15, it's outstanding, and 20 is totally awesome, excellent. Maybe what you see right now here on this screen could be like 1 to 15, yes, or 1 to 10 only contrast, and still we see the perfect image. We are very good at contrast as humans to see the differences. And if we go, of course, too low, close to 1, then we don't see, yes, because the values are becoming equal of the bright and dark. Yes. So this is the first thing. So the real contrast is way lower than what we see in the specification. That's why the contrast itself in a specification is not the most important part for bright environment. Yes, if we work in a dark environment, maybe we will look in the contrast, and let's say display that would be 1 to 1,000 would be better than display that is 1 to 500. But in the real case, real life case, when we have a bright environment, then these two displays will look pretty much similar and will be readable similar, because the real numbers will be way lower, and it's connected actually with other factors, not the contrast itself. Yes, so here we have a little bit more, some calculations. So as you can see, if we take the typical newspaper, we can expect contrast 20 to 1 in the sunlight, which is very low. Yes, again, but perfectly readable, and we would say that the newspaper is one of the best that you can see and clearly read. And then we have some information about the notebook, that the brightness is lower, and some formula that is calculated here. We will go into details of how to calculate later, but as you can see, with the typical notebook, that will be 200, maybe 300 candela brightness. Nowadays the notebooks are going into higher brightness. Then we can expect very low contrast. Yes? So that's why it's very hard to read this kind of notebook in the sunlight, or like work with it. Yes. So here we go a little bit more into details, and we have example with the numbers of a display. I would say like mid brightness display, yes, which is like 400 candela in our example. As you know, our high brightness IPS displays, they are 1000 candela by standard, but here we have on purpose a lower brightness for calculation. So let's say we have 400 candela and we have 400 contrast ratio for easy calculations. Then we take it outdoor to the sunlight, where we can expect about 10,000 candela brightness of the light, and then we, let's say, assume for this calculation 4.5% reflections. That means the surface of the display will reflect 4.5% of the light that is coming. It's of course mainly sunlight in this case. So how much it will reflect? It will reflect about 450 candela, and it will reflect on all the surface. So on the white parts, the bright parts, and also on the dark parts, it's also reflecting. So whatever we had before, and what we had before is this. We had 400 candela, and let's say because the contrast is 400 by specification from a factory, we know that the dark part is a 1 candela. Yes, if we remove the reflections, we are in a dark room. We have 400 divided by 1, we have 400 contrast. Yes, so that means the bright part of this display is 400 candela. The dark part, if we will switch off the pixels, we will have 1 candela. Yes, so we have 400 contrast. But if we go outdoor, we need to add the reflections, and they are added, as I said, into the whole surface. So into the bright part we added, and also we added to the dark part. And then this number is completely different. So we go down from 400 to 1 to 2 to 1 only. So as we know from previous slide, 2 to 1 is rather unreadable, or like uncomfortably unreadable. I mean, it's hard to read or like see the content. We don't like this kind of displays to look at, because we need to like make the effort and think what is there. Yes, we don't see it clear. So it's way too low. So how we can improve that? We can do actually two things, the two important factors. First thing is easy. We can increase the brightness. Yes, so we go up. If we go to, for example, to 800 or 1000, we'll have like, you know, something like 3 to 1. Or what else we can do? We can decrease this number. That is a reflection rate. So we can change the surface of a display and make it to reflect lower. That's why we sometimes use coating on the glass, for example, that would be anti-reflective. So for example, from 4% we will go down to maybe 1%. So this number will go to 100. Yes, if we will have 100, fast calculation would be, you know, 500 divided by 100. This will be like 5 to 1. So if we will decrease only this surface without even changing the brightness of a display, we are able to go with the contrast from 2 to 1 to 5 to 1, yes, which will be actually good enough, or even perfect in a sunlight condition, to have the 5 to 1 contrast ratio outdoor display. Yes, usually we do both, so we try to increase the brightness and we try to decrease the reflections as much as possible, because the reflections, especially in the outdoor cases, they are high, because there is more layers we need to put. It's not only a display that we have outdoor, but we need to protect the display. So usually we add additional glass. If we have additional glass, and often this additional glass is not optically bonded to the surface of display, so we have air in between. That means we have more reflections. We have from the glass itself, from the glass to the air, and from a display again. So we have like sometimes even 10% of the reflections, or even more. Yes, that's why we need to increase the brightness as well. It's not that easy to handle. Yes, so this contrast is not good enough, and here we have example with increasing the brightness. Yes, so here's just the calculation. If we go to 1500 candela without lowering the reflections, we will have contrast 4.3 to 1. Yes, so again, from unreadable to readable. Yes, just by increasing the brightness, as I said before, we can also decrease the reflections. Yes, that's the other way. Yes, here we have a little bit more detailed what I was talking about in a minute ago about the reflections. Yes, so I said in typical outdoor environment we have a display, but we need to protect it because it's outdoor. So we need to protect it from vandalism, but also from environment itself, from the water, dust, and everything that we can expect outdoor. So we put additional glass. Sometimes it's just cover glass, sometimes it's a glass with the touch, depend on the application, and they are usually separated with the layer of air. It have a lot of benefits, like mechanical benefits, because it's easy, it's cheap to assemble this way, and also if the glass become destroyed and maybe the display is still okay, we can just replace easy the glass. If it's outdoor, it's sometimes very useful. Yes, so something may happen to the glass, and we may easily replace it without let's say replacing a display. But this, from optical point of view, this solution has a lot of disadvantages. As I said, we have a lot of reflections. Yes, so we have a reflection on the surface of the glass, and we have reflection inside the glass, that is like from the glass to the air, because we have, we change the environment. Glass is different environment, optically different environment than the air. So we have a reflection again, and we have a reflection from a display itself. So we have, many reflections. This arrow should be here, actually, would be better. So from the glass, from the back of the glass, and from the display itself, yes? Pretty high reflections. And the other solution is to add optical bonding, yes? So if we add optical bonding, that means we remove the air in between the display and the cover glass. And this material here, of course, is like the close possible to the glass. So from the light point of view, it's the same environment. If we don't change environment, we have no reflections. Yeah, like if we have like a big piece of glass, inside there is no reflections. Once the glass is inside the glass, it's no reflection. So if like from the light point of view, it's just the same environment, there will be no reflections, yes? So optical bonding is removing quite a lot of reflections, and also is improving the brightness of a display, because the light is not only being reflected, but it's also coming out from a display itself. If we have this situation, the light from a display is being reflected here on this surface, so we lose a few % of the brightness. And here, the light just go out, yes? And it's only reflected on this surface, so less reflections both sides. Yeah, here we have some more detailed explanation, yes? Yeah, and here we have this, what I was trying to draw before. Yes, so this is this situation with the display. So light going out from a display, of course, like 95% will go out, but 5% will be reflected here, and some of it will go eventually out, some not, and it's like blurring the display a little bit. This image is way more clearer. If you had a chance to compare air bonded display and optically bonded display, you will see that the colors are better, more vivid. The image is literally more clear in this situation. It's because the whole light is just going out, yes, without any reflections, scattering, or anything like that, yes. Here we have some a slide about the coating, yes. So the coating is adding extra layer to the surface, yes. Usually it's a glass, so we add this coating to the glass to decrease reflections, yes. I told about this before, so we can have 4 or 5% from typical glass reflection. If we add something that we call AR coating, that is anti-reflective coating, we will decrease this number, maybe to 1%, maybe to 0.5%. That would be very good, yes. In many cases, in practical number will be like between 1 and 1.5% after adding the anti-reflective coating, yes, which you already know that going from 4% to 1% it's a big difference in a contrast, yes. So something that we will eventually get as a user of a display, yes, as a viewer. Okay, here is just some reminder of our display lines. So first we have our old generation display line that was based on a TN glass, so twisted pneumatic standard glass, and I would say like mid brightness. When we were introducing this line like years before, this brightness were like industry higher end standard, yes. So most of the displays at that time were like 200 to 300 candela. Our displays were higher, they were like 500 to 600, as you see, the brightness, but still it's like too low nowadays. That's why we decided to introduce a new line. We changed the glass from TN to IPS to have all the viewing angle possible, and also to have better colors. And we also at the same time increased the brightness to go to 1000. 1000 is pretty universal number. I would say that we can use a display indoor in very bright environment, even the brightness, even if it's like a medical room maybe with a bright, or like industrial place where we have a lot of light, or we have even the coffee machine that is maybe close to the window and we have a sunlight coming from the window, then with 1000 candela we are able to make a perfect image and clear display. And this 1000 candela also allow us to build like outdoor devices, provided that we keep the reflections low, either by maybe adding some shadow, so not having the direct sunlight, or having, for example, some additional anti-reflective layer on the last surface. Yes, that will be typically glass. Yes, and as you can see in this table, if we add something on top of a display that is a typical touch screen, then the brightness go lower because of these reflections. Yes, so the glass is not perfectly transparent. The typical glass maybe has like 90, 95, 97% of transparency, so few percent we lose in the glass itself, the rest we lose because of the reflections. And as you see, if it's air bonded, we lose more comparing to optical bonded, we lose less, yes, because there is no internal reflection. These numbers are very, let's say, conservative. Actually, in like real world, they are typically higher, but this is the lowest you can expect. Yes, I would say that typically here will be 850, so 15% down, and maybe here will be like 10 to 12% maximum. Yes, but we try to be conservative. This is the lowest you can expect from our display with pickup and pickup optically bonded. Here we have also, in the old generation line, we have also cooperation with the resistive touch, and because resistive touch include more layers, we have like another air gap which is necessary for us to press, because resistive need to be mechanically pressed. We have even lower brightness because there is more reflections than with typical pickup without optical bonding. So just a reminder, this slide. So now once we know how to make a display to be readable outside, so we know that we can increase the brightness or we can decrease the reflections, and we have the image that we can see, we need to think how to make the display to operate outdoor. Yes, and this is all about the temperature. So as you know, our standard operating temperature displays that we offer are -20 to 70. I would say this is an industry standard. This is like standard operating temperature. And the storage, of course, is a little bit higher. Actually, some of our displays, for example, 7-inch for sure, was tested like -30 to, as I remember, I think 80 or 78 degrees. It was working. Yes, so the real practical value is even higher, but this is what we guarantee by spec. But for real outdoor LCD, it's too low. It's too low on two ends. So -20 in many cases is not enough. Maybe -30, -40 would be good enough to like have outdoor display worldwide. Yes, maybe in Scandinavia or somewhere else, we may expect lower temperatures than -20. And on the high end, it's also a problem because if we are outdoor in the summer and we have a direct sunlight, the surface of a display can go higher than even 70 or 80 degrees. Yes. So we need something different, and we need actually different technology, because what is happening here with a typical LCD, we have this liquid crystal. Liquid crystal, it needs to be liquid to work, and below this temperature it starts freezing. That means like becomes solid, and the crystals cannot move or move very slowly. And above this temperature, it changed the phase. Yes, so the phase that we work normally, like in this range of temperatures, let's say -20 to 70 degrees, we have the phase that we call nematic. So nematic phase is a phase where the light can be operated, let's say, by a crystal. So as you remember from discussion about how the LCD works, liquid crystal has the ability to change the polarization of the light, but it needs to mechanically move the crystals inside this liquid crystal cell, and it needs to be in this nematic phase. Yes, so below that we become solid, we cannot move, and above that, if we go, let's say, above 70 or 80 degrees for typical display, sometimes the border is only 50 degrees for consumer grade products. If we will go to isotropic phase. And isotropic means you cannot change the polarization of the light anymore. It becomes like all the light can go through this liquid crystal, and you cannot control it anymore with the voltages or anything. So basically you can't like switch on and off pixels. Yes, that's why we have something that we call high TNE displays, and it means high, yes, TN, which is like, you know, twisted nematic, isotropic. So this point, nematic to isotropic, we want to put as high as possible. So for consumer, it will be maybe 50 degrees. And we will go from nematic to isotropic. That means the display stopped to work. For industrial, will be 70, yes? And what we need is higher. And there are technologies, we call them high TNE technologies, that move this point even higher. And we should have it, yeah, for outdoor displays, marine, yes, automotive and military. And this is example from a UO presentation about high TNE displays and outdoor displays, basically. So we have two cells, two liquid crystals that we can use. One is like minus 20 up to 110 degrees, and the other one, the latest one, is minus 40 up to 110. So the same upper temperature. So in this range we are safe. So we can go very low with the temperature and it will not become solid, and we can go very high with the temperature up to 110 degrees and it will not become isotropic. So the display will be working. Maybe you have seen some displays that were used to outdoor, are used outdoor, and sometimes they become black. We call it the blackening effect. If they become like too high, that means the crystals become isotropic, and you can see maybe the part of the display is black or the whole display become black, depending on temperature. The good thing is that it's not breaking the display, so once the temperature drops, it go back to the nematic phase and the display work again. But in a high temperature you cannot see anything on a display. It's basically is not working. Yes. So if you will go to the roadmap of AUO, for example, you will see which exactly displays has this, you know, high temperature liquid crystal. Yes, high TNE LC we call it. So high temperature nematic isotropic liquid crystal, to be precise. Yes, so you can see which ones you can like use in outdoor environment. And here we have example from a data sheet of a display with high temperatures. So as we said, it's a liquid crystal from minus 20 to 110. So this is the latest technology, but you need to be careful. This is only about the surface of a display, so a TFT glass itself. So we can have the sunlight going to the display and increase the temperature of the display, but the whole display as a module, we need to be careful. And in, let's say, the operating temperature, depend on the display, of course, can be lower, can be as low as 0 to 50 or minus 20 to 70. So we need to control that. Maybe we can have two temperature. What does it mean? That means if we will use this display outdoor, we are safe from the sunlight. The surface of the display can go very high, but maybe our ambient temperature inside our housing, yes, because we have some kind of enclosure. Let's imagine it will be a totem or something. Inside we need to like control the temperature to not go too high. Yes, maybe 50, 70 will be maximum. So there are usually maybe a fans inside to remove the heat from inside or something like that. But in typical use case, we have a computer inside and we have more devices that cannot work with that high temperature as 100 degrees. So we control this temperature anyway. Yes, so it's not so bad. This temperature just cannot be too high inside, and for sure cannot be that high as a liquid crystal itself can withstand, yes, which is 110 degrees, yes. So that will be all for today about the contrast and the brightness. Maybe one more information: if you, for example, buy a laptop today, I mentioned that old laptops were like 200 candela only, or 300 candela. Today you can find in a specification some of the manufacturers show this, and some of the shops are showing these numbers, like the brightness. So be careful and look on this number, because this number will determine how good your laptop will be, let's say, outdoor. There are laptops on the market today that will have 1,000 candela or even more. If you are looking for a new device, for example, that is my recommendation. It's also about the mobile phones. So we had this like low brightness mobile phones, maybe 300, 500. Nowadays, the standard will be around 1,000 candela, but there are phones on the market that already have like 1,500 or even 1,800. That means if you are on the sunlight and you have the peak of the sun, you'll still be able to see the image clear. Of course, the battery will be drained faster, but sometimes it's not that important for you. Maybe you want to check something 5 or 10 minutes to read something and you want the image clear. So just like be aware of this number. It's pretty important when you buy a new device, yes, to have the high brightness which are nowadays available. Okay, thank you very much again. Thanks.